Thank you. I'll be talking about design and astronomy. And there really are just two explanations of how we got here, we and the world around us. Either it all happened from a purely natural, purely physical process, which, for lack of a better term, I would define as evolution. Now, I know that the evolutionary biologist would get upset with that usage that way or that definition, but that's a very restrictive use of the word evolution. Evolution really is a concept that's used in geology all the time. It's also used in astronomy quite a bit. We talk about stellar evolution. So I like to define evolution in a very broad sense, so it covers all the various disciplines. So I would define it as a purely natural, purely physical process. Notice, of course, that if it is purely natural, it cannot be supernatural. If it's purely physical, it cannot be metaphysical, which of course would rule out the existence of God, it would seem. The other possibility is that we have a supernatural process, the opposite of the purely natural one. And of course, that's talking about creation. Now, one limitation of talking about, say, intelligent design is it doesn't tell you who the creator is. Doesn't mean that this isn't useful. It just simply means it's inadequate to tell you many of the things that we need to know. And this gets back to Romans 1:20, which of course as I was pointed out just a few moments ago, is a key verse, a theme verse for this conference. And many times people ask the question, well, is it really important what we believe about this? After all, if we all have Jesus in our heart, does it really matter how the world came to be and how we came to be? Well, I think the answer to that is yes. And there are many reasons for that. One is the fact that many important themes, even salvation foundations, are introduced in the first few chapters of Genesis. Why we're sinners, why we need redemption, why we die, those kind of questions. And if you don't have a creationary worldview on that, then you have an evolutionary worldview on that, and it really works against your theistic and Christian beliefs. And I would say, I'll go further to say that how we view the origin of ourselves and the world around us colors how we look at the world. It gets to your worldview. How do you view things? What's the filter that you have? How do you interpret things? And the evolutionist is going to look at the world very differently than the way a creationist would, because you see, creationists see design and purpose in everything around us because we see that things were intended to fulfill some purpose and some design. And it's our job many times as creation scientists to attempt to identify what those purposes and designs might be. Sometimes it's obvious, sometimes it's not so obvious. Just because we don't see the design doesn't mean that there isn't any there, it just means we haven't figured out what it is yet. But the evolutionist, on the other hand, particularly in biology, sees chance and struggle, and astronomy more like random things going on. There is no design, there is no purpose, because there is no body behind this, no creator behind this, intending anything by things. Things exist merely because they exist, no more, no less. And this is because we begin with two very different assumptions. One is theism, the belief that there is a God, there is a creator, and the other one is atheism. And again, I want to drive home the fact that you can become a creationist and still not know the Lord. I actually know several creationists and Christians who were creationists for a while before they were Christians. They came to the realization there must be a creator, and then sometime later they said, well, wait a minute, if there's a creator, then maybe he has some demands upon my life, and they began seeking that out. So creation itself, the study of that and conclusions about that can lead one to salvation. There is a way of creation evangelism, as it turns out. Now let me illustrate this by three photos here. This is a photograph, a very famous object in the sky called the Horsehead Nebula. It is a star. It's located in the constellation Orion, and it's below the leftmost star of the belt of Orion. It's not nearly as bright as it looks here. These kind of photographs are long exposures. I've seen it once with my naked eye through a pretty large telescope, and it didn't quite look like this. I could kind of see this, but it's not nearly as good as the photographs would lead you to believe. And you see the red color across the top there. That's due to hydrogen emission. It's caused by excitation of electrons in the higher levels coming down to the second orbital in the hydrogen atom. And you can see across the bottom, it's a bit dim down there. That's because you have a lot of dust particles. These are microscopic particles in a big cloud, pretty thin, but yet pretty large in size. There's a lot of dust there, even though it's a very fine vacuum down there. And around that star in the lower left, you see that big blue glow. That's light scattered off of the dust particles there. It turns off scattered light off the dust particles appears blue, and hydrogen gas generally produces that red color. And there's a big bank of dust below there on the lower half of the photograph, blocking our view of more distant stars. And on the upper half, you don't have nearly as much blockage. If you look across there, you'll see the density of stars there in 2 dimensions is greater. You see more stars up there than you do below because you're able to see past much farther, and you're seeing more background stars. Those stars you see below, those are all foreground stars. And then there happens to be a little appendage sticking up out of that big dark gas cloud. We don't know what shape that little appendage has in 3 dimensions because we're only seeing this in 2 dimensions, but it does give you kind of a horsehead shape, and that's why we call this the Horsehead Nebula. Many of my astronomy colleagues assure me that if they ever find the other half of the nebula, they're going to name it after me. Okay, this is a photograph of comet Hale-Bopp, I believe, taken back in the late 90s. 23 years ago now. It was a remarkable comet, and you can see the brightness there, the background stars. You can see that there are 2 tails. There's an ion tail that's that very amorphous whitish, maybe a little yellow tint glow, and above that you can see a bluish tail, a little bit fainter with streamers running through it. Why do you suppose it looks blue? I just told you a moment ago, it's dust particles, and they're scattering sunlight. The light is off to the left, and as light hits those dust particles, it scatters off, and it scatters off blue more than it does other wavelengths. So it appears bluish to us. The gas tail is the ion tail. That consists of various ions that have been ionized by the gas particles, gas molecules, or atoms that have been ionized by the sun's radiation, and they then recombine, producing that bright glow. Now, both tails are going from left to right. It's important to note that that's not the direction, the indicating direction the comet is going. The tail always points away from the sun. That's because the solar wind pushes the ions away from the sun, and solar radiation pressure pushes the dust particles. We recently had a little comet come through, comet Neowise. I saw it on many mornings and many evenings. Took photos. It's still visible in the evening sky, but you need binoculars to see it. I took some photographs of it, and all of those photographs, the tail is pointing away from the sun. So this thing is powered, if you will, by on the far left, and the head of that comet, the brightest part there on the left, by a little chunk of ice and dust. Hale-Bopp is about 25 miles across, we think, one of the largest comet nuclei we had ever seen. And comets follow very long elliptical orbits. They spend most of their time very far from the sun where it's very cold. Once each orbit, the nuclei come very close to the sun, and the heat from the sun's radiation causes the ices to sublime. When I say ices, it's water ice, but also methane and other things we think of as being gases many times. And they sublime. It goes directly in the vacuum of space from being a solid to being a gas. And then, of course, then the solar wind and radiation push it around. Comets are interesting. There's not much there, but there's a lot to see, it seems like. And they also have some things to say about the age of the solar system, which, of course, is not my subject today. And then I have here the photograph of the Ring Nebula. This is one of my favorite objects to look at, particularly this time of year. It's up in the summer for us here in the Northern Hemisphere. And it looks like a little smoke ring. It's once we thought it was kind of a bubble shape. Now we're thinking it's more like an hourglass shape when we're looking down the length of it. And if you look down at the center there, you'll see a faint star. You need a very large telescope to see that. I've never seen it. Of course, photographs with long exposures can pick them up. And I believe what happened is in the past, this star blew off its outer layers. When I say it blew them off, I'm not talking about like a huge eruption, explosion of some sort. Instead, we had what are called stellar winds. I mentioned the solar wind earlier. That's an outrush of charged particles from the sun. at the rate the sun's losing material, it would take even over 10 billion years. It wouldn't lose very much. But some red giant stars are seen to lose as much as, maybe a few thousandths of a solar mass per year this way. So they're losing at a prodigious rate. And we think that the star in the past blew off its outer layers. So it's a very interesting object. It's a really prototypical of a class of objects we call planetary nebulae. It's most unfortunate because they have nothing to do with planets. It's just through a small telescope. They look like a little disk, which superficially resembles the appearance of a planet. The Dumbbell Nebula is another example of a planetary nebula, which is also visible in late summer and into autumn. Now, I just showed you 3 photographs. I want to ask you, what did you see? Well, most of us would see beautiful photographs. I think one of the things that gets people excited about astronomy is the many, many remarkable photographs you can see. The beauty and wonder looking at it through the telescope can be exciting as well. It's probably the thing that turned me on astronomy 60 some years ago, because there's just a lot of beauty there and wonder. If you can't look at these sort of things or look at things through the telescope and be just really wowed by it all, then there's something wrong with you, I do believe. And then I also talked about some of the physical processes going on there. And when I was in grad school, we spent whole semesters in a class or two where we just talked about and discussed and described the physical processes going on. We can use those physical processes to probe conditions out there in space. We can figure out what things are made out of, how much density they have, how much temperature, all those kind of things. Very subtle things that you might not think at first could be done, but can if you know something about the physics involved. That's why we have the term astrophysics, because it's a combination of modern physics with astronomy, which didn't really exist until a little over a century ago. So most people see the beautiful photos. The people who are scientifically inclined, physically inclined, they see that, and they see the interesting physical processes. But if that's as far as it took you, then you've missed the entire point, I believe. What you should see is the Creator's handiwork, as Psalm 19:1 says, and it was brought up again in the introduction this morning. We'll repeat it again here. The heavens declare the glory of God, and the sky above proclaims his handiwork. This is a parallelism coming from David, and he spent a lot of nights, I'm sure, as a shepherd there in the Judean hill country, and at night probably looked up in the sky and was just simply wowed away. I'm always amazed when I get off to a really dark, clear place with some elevation, particularly. I like to just lay there and look at the sky. It's incredible to drink in. But think how much more we should appreciate this today, because back then they didn't have telescopes. They didn't have all the technology we have. Today we do, and yet many people don't even know about these things. Now, I do want to caution that design is not a conclusive argument with most people. It ought to be, but it isn't many times. And here's the problem. If you are already a theist, if you believe that God exists, you believe that he's created us and the world around us, then it's quite easy to reinforce that belief. You're going to say, okay, I can see that design. I can see that all that purpose being fulfilled in the creation around us. But if one is not a theist, who doesn't believe in creation, then you're likely to ignore it or explain it away. You're going to say, well, that's just this, or it's that, coincidences, all those kind of things. And it's very frustrating to deal with people, because it does not seem reasonable or rational to me. But of course, it's not really a head problem at all. It's a heart problem, because you see, if there's a creator, then you realize that you're beholden to him. He may have expectations on your life. And if people are not willing to submit to a creator, then they have a problem. And so the way they have to rationalize it can be quite irrational, but they think it's rational in their own hearts. Let me go through a few examples here. Here's a photograph of a total solar eclipse. I took this 3 years ago. I was in Oregon, east of the Cascades, for this eclipse. And this is about I can't remember the exposure time on this. I used the Questar telescope, which has a focal length of almost 1,400 millimeters. So it's a whale of a telephoto lens. And you can see there's some prominence and sticking out on the right side, those little loops that you see. And you can see the inner corona showing up here. I couldn't get most of the corona because The focal length was just way too long. You can't get but a little bit of the sun, the whole sun, and a little bit of the corona there. I'd need a much wider angle to get the corona. And I will tell you this: this is my second eclipse. I saw one back over 40 years ago, and no photograph, no video does it justice. You really have to experience one. I went to my first one back in 1979, and when I saw it, I realized, okay, now I get it. I really get it, that what this is all about. And people who saw this eclipse 3 years ago might think, okay, that's great. Don't need to see another one. Well, I heard for years that every solar eclipse is different. And after having seen 2 of them now, I can tell you, yeah, they are very, very, very different. They're similar, but yet wonderfully different in every way imaginable. Totality is most remarkable, most beautiful thing I have ever experienced. I think that it is the most incredible thing in all of creation. And people who know me well will be amused. I have a tendency to do something when I am totality, having gone through it twice. Very quickly, I shut up. I don't say a word, which, again, people who know me well think, really? That's amazing. And it is, because I'm just so taken in by it, and so many things going on, I want to drink it in. And the first eclipse, I don't think I said 2 words the entire time during totality. The most recent one, I was leading a group, and we did a video, and you could hear me at first saying a few things, trying to direct people to look for stuff. But after that, I just didn't say anything. We have an eclipse coming up in 2024. I'm curious to see what will happen at that time, but it has an amazing effect upon people. A friend of mine took this photograph of the same eclipse, wider angle, and you can't see the prominences here because it's too long of exposure, but you can see the corona. The corona is an outer envelope of the sun, outer atmosphere of the sun, which contains very hot particles. Not a lot of heat there, but high temperature. And you can see the streamers there mapping out the magnetic field of the sun. And the bright star Regulus is off to the left in this photo. And I took this photograph way back in 1979. This has been scanned. It was a 35 millimeter slide. And this shows what we call the diamond ring effect. You will see the diamond there on the side and the ring on the right side, and then the ring all the way around. This occurs very briefly before and after totality, just for a fraction of a second. I was snapping away photographs at the end of totality, hoping to catch it, and I did. And I've been warned that maybe it might fry my camera if I tried it at the eclipse 3 years ago. It turns out I probably it wasn't an issue, so I should have tried. Next time I will. But then I told everybody to look away, and my wife and my son, they didn't, and they said they saw this. I am jealous, but at the same time, I think they're insane, because at first, that little bit of sunshine can be very harmful for your eyes. I don't recommend you try looking at it at all. All right, total solar eclipses. An interesting design features coming in here. For instance, the sun is 400 times larger than the moon. And yet, if you look up in the sky, you'll see that the sun doesn't look 400 times larger, does it? In fact, what makes total solar eclipses possible is the fact that they have about the same size, about 1/2 degree angle subtended. So how can that be? Well, it's because the sun is about 400 times farther away than the moon. So if it's 400 times larger and 400 times farther away, that means that it compensates exactly. And so the moon, when there's a total solar eclipse, just barely covers up the sun. And think about it: if the moon were a little farther away or a little smaller, then there would be no total solar eclipses. We wouldn't be having this part of this conversation, would we? On the other hand, if the moon were closer or larger, or if you change the sun's distance or size accordingly, then you would have more frequent eclipses, and they would be grossly over total and not as spectacular as it turns out. The moon just barely covers the sun. You get spectacular total solar eclipses. Also, they're extremely rare. We have a total solar eclipse on average about once every year and a half somewhere on the Earth. Usually it's in the middle of the Pacific Ocean or Greenland or Antarctica or some Siberia. It was amazing 3 years ago. It was the first coast-to-coast eclipse in a century here in the United States. I read once many years ago, I wish I could find the quote, that on average, a location on the Earth experiences totality about once every 4 centuries. So obviously, if you're going to see totality, you better either be very lucky in time and place, or you're going to have to plan to go someplace to see it. And None of the other 100 or so natural satellites in the solar system do this. I'm using the term natural satellite. Sometimes people use the word moon, but keep in mind that the moon is the proper name of the Earth's natural satellite. So it's not proper to call other natural satellites of the planet's moons. It'd be like, people calling me Kurt and calling Steve Kurt, because the only creation scientist they know is Kurt Wise. So we should be careful not to use the moon's name that way. But if you look at it, there's over 100 natural satellites of the other planets, and either they're too small or too close to too far from their planets to produce total solar eclipses, or they're too large and too close, and you get grossly over total eclipses that are pretty common. And what I find remarkable is we combine this rarity and beauty and wonder only on this one planet, and it's the only planet where it matters, because it's the only planet where there happen to be creatures, you and me, that can appreciate this beauty and wonder. And by the way, do some science during this time too that can't be done any other time. Now, you can call that a coincidence, and indeed, that's exactly what many people do, because they don't want to entertain the possibility of design, and that's their only out. But I have to ask, how many coincidences are you allowed to have? If you have one coincidence, that's a coincidence. But if you have 2 and 3 and 4 and 5, eventually you have to start wondering, well, maybe these aren't coincidences at all. Here's a photograph of the moon. And the moon is a fascinating object. Over the years, I've used to not be that terribly interested in it, but in more recent years, I've gotten more and more and more interested in it. And several interesting features about it. I just want to share one with you, a couple with you today. First of all, the moon is fairly large compared to the Earth. Now, I don't mean the diameter. The Earth is about 4 times larger than the moon. The Earth's about 8,000 miles across. The moon's about 2,000 miles across. Look up in the sky sometime. You see the moon. Just imagine it's the width of the United States from the East Coast to the West Coast. That gives you an idea. Now, what I'm referring to, rather than size, is its mass. The Earth's mass is about 81 times that of the moon. Well, the moon's about like 1.5% the mass of the Earth. And you may say, well, that doesn't sound like very much. And indeed, it is a large ratio in favor of the Earth. However, when you look at the other natural satellites of the other planets, we find something very startling. It's usually in the tens of thousands or millions to 1. I think the closest ratio is about 4,000 as opposed to 81. So when you talk about do a mass comparison between the natural satellites of the planets and the planets themselves, there's no comparison. Usually the planets far outweigh, as it were, their satellites. But in the case of the Earth and the moon, there's a close ratio there, actually, closer by far than any other planet and its natural satellite. Well, that's interesting, but what else is there? Well, the moon orbits in an unusual way. It orbits in the same plane as the Earth orbits the sun. We call that close to that same plane. We call the Earth's orbit around the sun the ecliptic, or the ecliptic plane. And there's also another plane we see in the sky called the celestial equator. It lies above the Earth's equator. Now, everybody knows that the Earth's axis is tilted 23.4 degrees. So the angle between the ecliptic and the celestial equator is 23.4 degrees. Now, what's fascinating is that many of the satellites, and most of the large ones in the solar system, they orbit in the equatorial plane of their respective planets. A few others just have weird orbits, but of the 160, 200 known natural satellites in the solar system, the only one that orbits in the plane of the solar system rather than the equatorial plane or some other weird plane is the moon. Now, that's weird. I mean, it's a unique in that respect. And again, you may say, well, so what? Well, for one thing, it tells us the origin scenario for the moon is likely very different from the others. Now, I'm not just talking naturalistically, I'm talking about creation as well. If you want to make up a scenario for how the moon came about naturalistically, it's going to be unique among all the natural satellites in the solar system. And how many times do you have to invoke something unique about the Earth before you begin to realize that maybe the Earth is unique for a reason? But more to the point, I believe the origin of the moon is unique because of its purposes it has to serve. It has to do certain things on this planet for mankind and for plants and animals that no other natural satellite in the solar system has to do. It has to do with time, tides, regulation of time, all those, providing light on the Earth, all sorts of things. But there's something even more fascinating. I remember I mentioned that 23.4 degree tilt that that the Earth's axis has. That is not fixed. It turns out other objects in the solar system, Jupiter, the sun, other objects, their gravity tweaks and pulls on the Earth. And over some period of time, the Earth's axis that tilt should change. It could go over a long period of time from being 0 to being 90 and back again. Now, think about that for just a moment. If the tilt were 0, there would be no seasons. That would not be real good. It wouldn't be that bad, perhaps, but it wouldn't be ideal. But on top of that, if the tilt were, say, more than 45 degrees, then portions of the planet would be simultaneously in the tropics and in the Arctic or Antarctic at the same time. For instance, the tilt of Uranus is 98 degrees, which means most of its surface is simultaneously in the Arctic or Antarctic and in the tropics. That would cause wide annual swings, which would be problematic for plants, animals, everybody. I can't fathom what it would be like. It would be a disaster for life, I am convinced. So how is that prevented from being a problem? Well, it turns out the moon's presence stabilizes the Earth's tilt so that it waffles around over about 2 degrees. It can't change any more than that. And on 23, 24, 22 degrees, that's as much as it can go. It goes back and forth, waffles around over time, so that it stabilizes it. Well, there are 2 things that are required to stabilize the Earth's axis this way. One is that the mass has to be relatively large. The moon's mass has to be relatively large compared to the Earth. And the other, it has to have this unique orbit in the ecliptic plane, not in the equatorial plane. If one or the other is not present, this mechanism doesn't work. If the moon isn't present, this mechanism doesn't work. So you can see you've got more than just one coincidence here. You've got a moon, a satellite, first of all, the moon. Second of all, it's got the right kind of mass. And third of all, it's got the right kind of orbit. And again, you can chalk that up to coincidence, but how many coincidences are you allowed to have before you begin to realize that maybe this isn't a coincidence after all? Also, this little sidelight here, I think the moon made physics possible. What I mean by physics is our understanding of the physical world. There's a whole branch of science we call physics. I study it quite a bit, taught it quite a bit. It's the dealing with the physical world, dealing with forces and masses and accelerations and so forth. And the person who wrote the book on this quite literally was Sir Isaac Newton 350 years ago. He wrote a book we call the Principia, the Principles of Natural Philosophy and Mathematics. And what did he do in that book? Well, he laid out calculus. He invented calculus. He invented his 3 laws of motion. He invented his law of gravity, talked about the theory of light a little bit. And by the way, he did all of this work by the time he was 23 years old. Amazing man that he was. Incidentally, also, he did it during a plague year. They had the bubonic plague sweeping through Europe, and he isolated himself for about a year to avoid contamination. So maybe we can relate to that. I have to ask people who are 23 or older, what have you done in this plague time we're having? Have you done anything significant at all? I didn't think so. I haven't either. All right. Why does this make physics possible? Here we have a photograph of the Earth and the Moon taken together from one of the probes, I think Voyager probe that went to the outer planets. And it's right to scale. They did, however, have to tweak the brightness because the reflectivity we call the albedo of the Moon is very low compared to that of the Earth. But the scale of size is right there. Now, we happen to know that the Moon is 60 times farther away from the Earth's center than we are. Another way of saying that is the distance of the Moon from the Earth's center is 60 times the radius of the Earth, 30 times the diameter of the Earth. So keep that in mind. 60 becomes very important here. This information was known a long time ago. Actually, Ptolemy worked it out nearly 2,000 years ago, and Tycho Brahe even did it better about a little over 400 years ago, about 430 years ago or so. By the time Newton came along, he knew how far away the moon was. Eratosthenes in 200 BC had figured out the size of the Earth, got its circumference and radius down. So this is all ancient information by the time Newton comes along. Now, Newton calculates on the basis of his physics what kind of force was needed to keep the moon in orbit around the Earth. That was his big problem he was looking at. If it hadn't been for this problem, he probably would have never done these marvelous things I just described to you. You would have probably never heard of the guy, and we wouldn't have physics as we know it. The big question he was looking at is what force compelled the moon to orbit the Earth every month. People had known the Earth orbited the moon orbited the Earth every month from ancient times, and people had wondered, why does it do that? To some of the ancient Greeks, it was just just what celestial bodies do. But in the more modern times, people are going to ask, well, what's causing this? It must be a force of some sort. And Newton's great insight was the belief, the working hypothesis, that the same force that caused things to fall on the surface of the Earth, like the fig falling off the head and off the tree and hitting Newton in the head, was the same force that compelled the moon to go around the Earth every month. That was a great unifying concept. He was taking things in the heavenly realm and equating it with the same sort of physics that operated in the earthly realm, which is quite a break from Aristotelian thinking that had dominated for so long in the West. Now, other people had already measured the acceleration of gravity on the surface of the Earth. It's 9.8 meters per second squared, or 32 feet per second squared, depending on what units you want to use. Now, based upon his newly invented calculus and laws of motion, Newton was able to figure out what acceleration was required to keep the moon in orbit around the Earth. And his calculation was that it was 1/3600th of the attraction we feel at the Earth's surface. Again, we're attracted to the Earth's surface by a force, by acceleration that's 3,600 times greater than the acceleration of the moon going around the Earth if the same thing is going on, whatever it is that relationship holds. Now I ask you, look at that. Newton realized that probably distance was important, and he looked at those two numbers. He saw 60 and he saw 3,600. And what's the relationship between those two? The answer, squared. We're 60 times closer to the Earth's center than the moon is, and we're also attracted 3,600 times greater. And Newton didn't think that was an accident. He didn't think that was a coincidence. He said, aha, the law of gravity ought to be inverse squared. By the way, people have measured how much it's equal to 2, the inverse, the second power. It's something like to 19 decimal places, it's exactly 2. I suspect it really is exactly 2. There's a physical reason for thinking that too. If the universe being three-dimensional, 3 spatial dimensions requires that to be the case. So some people say, well, there's no design there. Well, it turns out, well, why is the universe 3 spatial dimensions? If you had any other spatial dimensions like 4 or 5 or whatever, this wouldn't work like this. And in fact, Newton went on to point out that only with the inverse square law do you have stable orbits. And again, you can say, well, that's just coincidence. But again, that begs the question. You have 3 dimensions of space. Why is this universe 3 dimensions of space? It could have been some other dimensionality, but it's just 3. Again, that's a coincidence, I guess. And the fact that the Earth even has a moon is coincidence, because without that, Newton wouldn't have had a big problem to solve, and we wouldn't have physics as we know it. And we would be living in a far more primitive society, because physics, when it was finally developed 350 years ago, took off. And much of the modern technology, such as the things that allow us to do this distance conference, are based upon that Newtonian physics. So I thank the Lord for the moon. I thank him for also a man like Newton, who could lead the way for so many of us. Newton was an incredible man, an incredible intellect. Well, here we have the Earth taken from space. You can see there North America showing up, most of the United States showing up there, and the Earth has some interesting properties as well. I'll just zero in on one of them here. Well, actually a few of them. I'll mention a few and then really discuss one. We're the proper distance from the sun. And again, Professor Wise last night talked about this a little bit. Astronomers today define a thing called the habitable zone around a planet. It's the narrow range around a planet where around a star, where if there's a planet with the right conditions, right atmosphere, right mass and composition and so forth, liquid water can exist. It's called the Goldilocks zone sometimes. If a planet is too close to its parent star, like say Mercury and Venus are, then it's too hot. If it's too far away, it's too cold. You don't get liquid water in either case, and liquid water is absolutely essential for life. So you have to be the proper solar distance. Well, guess where the Earth is? It's right smack dab in that Goldilocks zone, exactly where it needs to be. Again, you could say that's coincidence, but how many coincidences are you allowed to have? And then it also has the proper size and composition. You look at the Jovian planets; they're in the wrong place, but they have way too much mass and the wrong composition altogether. Venus and Mercury doesn't have enough mass, and so forth. Now, you want a nitrogen-based diatomic atmosphere. What that means is the atmosphere of the Earth is about 79% made of molecular nitrogen, consisting of two atoms of nitrogen bonded together. Now, I don't have time to talk about this at length, but suffice to say that astronomers today believe that this is the ideal atmosphere to have. In fact, if they're looking for life on other planets, that's the kind of planet they're looking for, a nitrogen-based diatomic atmosphere. You don't want polyatomics too much. Those are greenhouse gases. You don't want too much. You want a little bit of that, but not much. They've determined that the Earth's atmosphere is ideal. It's perfect. Again, it's just coincidence, of course, in the estimation of most people. And then liquid water has to exist. It's an abundant molecule. I'll mention this in passing. Water is probably, H2O is perhaps the most abundant molecule in the universe. It may be the second most abundant, but it's very common. We've detected it in lots of places, but we've never actually detected liquid water anywhere except the Earth. We have some hints that it might exist in a few places, but we've not actually observed it, never ever actually measured it. We find solid and gaseous water in all sorts of places, but we don't find liquid water. Again, a rare commodity, and the Earth has it in abundance. Well, the atmospheres, here I have the Earth right there, right of center. To the left of center is Venus. Notice it's nearly the same size, but its atmosphere is very different. To the right of the Earth is Mars. It's only about half as large as the Earth is, and it has a thin atmosphere, but not enough to really get the job done. To the upper right of the Earth is the Moon, of course. By the way, the Moon has the right distance. Mars and Venus don't, but Earth has the right. Moon has the right distance from the Earth, from the Sun. It's in the habitable zone, but it's dead as a doornail. We knew that before we went there with the Apollo program, but we kind of confirmed that by going there. And the reason why the Moon, even though it has the right distance, is it has almost nothing else right. The composition is wrong, the mass is wrong, it has no atmosphere, no liquid water, and on and on and on it goes. There's so many things wrong with the Moon, even though it got one of the important elements correct. To the far left is one of the satellites of the outer planets. It's a bit bigger than our own Moon, but still smaller than the planets there. And then on the far right is one of the largest asteroids, or minor planets. None of those are really suitable for life. Most of them don't have an appreciable atmosphere. The ones that do, well, their atmospheres are all wrong. And so I can say, like the rhyme of the Ancient Mariner, water, water everywhere, but not a drop to drink. We have it in abundance on Earth, but not on the Moon, not on Venus. There's a Magellan map, a radar-generated map of Venus. And of course, Mars, again, there's water there, but not liquid water. It's all solid and gas. It's too cold, and the atmosphere is too thin for water to exist. If an astronaut went there and opened up a container of water and poured it out, a portion of it would almost immediately boil away, and the remaining part would almost immediately freeze. It wouldn't exist as a liquid very long at all because of the pressure and coldness there. And there again is one of the satellites of the outer planets. Now we can do a comparison to other worlds, not just in the solar system, but elsewhere in the universe. And Venus is it's too hot. Mars is too cold. That's the reason why the Earth is sometimes referred to as a Goldilocks planet. And the moon, I've already mentioned, is dead as can be because of so many things wrong with it, even though it gets the distance right, whereas Venus and Mars don't. And then there are all these extrasolar planets that have been discovered. The first one was discovered 25 years ago, and now we know of more than 4,000 extrasolar planets. These are planets orbiting other stars. Been, since really 400 years ago, people have speculated, could there be life on other planets in the solar system, and could there be planets orbiting other stars? And they've played this game. They say, look, if planets are common in the universe, then think about all the billions and trillions of stars. And if just tiny percentage of those planets orbiting around those stars were harboring life or suitable for life, then you still have a huge number of possible civilizations or planets with life on them out there. So they want to play that little game of probability. And so we've been doing this a lot in the last 25 years. There's a artist's conception of the Kepler spacecraft launched a decade or so ago. And what we're looking for are planets orbiting other stars. And there's several methods of doing this. The one of the most productive has been used by the Kepler mission and now being used by the TESS, the Transiting Exoplanet Survey Satellite. That one, Kepler's been kind of decommissioned largely, but the TESS is still going strong as far as I know. And they look for transits. Well, what is a transit? Well, I can describe that for you in the next slide here. Suppose you have a star indicated by that yellow circle, and suppose there's a little planet orbiting around that little red circle, and that little ellipse you see there, that's the circular orbit seen of the planet around the star, seen almost edge on. Notice you have to be looking almost in the plane of that planet, the ecliptic, as it were, of that planet. Now, once each orbit, the planet would pass in front of that star, and it would, as it passed across, it would dim that star slightly. Now, I mentioned before, I've done more than 40 years, I've been studying eclipsing binary stars. These are two stars orbiting one another, where one star passes in front of the other one periodically. And in fact, it looks a lot like this, except the stars are closer in size, more similar in size than this. But you get a little eclipse. And across the bottom there is what we call a light curve. Brightness, you can see on the left there, is plotted vertically. Horizontally is plotted time. So when the planet is not passing in front, that is transiting in front of its star, then the light is constant. But when the star gets over to the edge and starts to impinge on the surface of the star, the light of the star will dim ever so slightly, and then it will recover and wait until the next time. To put this in perspective, the sun is more than 100 times the diameter of the Earth. So if you viewed it from a great distance, say another star system, the surface area would be 10,000 times greater than the Earth's surface area. And so if you happen to be on an alien world looking back towards the sun, and you happen to lie close to the ecliptic, so that these can happen once each orbit, once every year, for about 8 hours, the sun would dim by about 1 part in 10,000. That's not much of a drop. It's 1/100th of 1%. However, Kepler could measure 1 part in a million. So measuring a planet the size of the Earth would have been a cinch, provided that we were in the orbital plane. And it discovered a bunch of such planets orbiting around other stars. The fact that it discovered so many, when it depends upon the inclination of how we're looking at it, most of these orbiting planets would escape detection because we wouldn't be looking at their orbits nearly edge on. So we think there's probably a lot of planets out there. We're just discovering just a few of them, and TESS is even more sensitive than Kepler was. Kepler was measuring a few 100,000 stars every 20 minutes with this accuracy. It's amazing technology we have today. So I just showed you the kind of idealized situation on the top there. The bottom shows you a real eclipse curve. This is actually a transit curve observed, I think, by Kepler. And you can see the data is kind of noisy. Actually, this may have been ground-based. It did kind of noisy, and then it bottoms out and recovers again. And by studying how often this happens, we can figure out the orbital period, and hence infer the distance of the planets from the sun, the star that they orbit. We don't know. We can actually get an idea of their sizes too, but beyond that, we don't know. We don't know their masses, which is pretty important. We have to guess at those sorts of things. So, question is, why do we look for extrasolar planets? Well, they want to prove that planets in the universe are pretty common, and they want to prove that solar systems are common. These are systems of more than two or more planets orbiting around stars. We found like 4, 5, 6 planets sometimes orbiting around a single star. We want to look for that because there, of course, there are 8 planets we know of orbiting around our own sun. So we hope that other solar systems are common. And then beyond that, to prove that Earth-like planets are common, because that's the gold standard. You got to have Earth planets-like planets in order for life to exist. And ultimately to try to prove that life is common. That last part may be the more difficult to try to prove, but that's the push they have. So what have we found so far? Well, we found that planets are common. If you find 4,000 of these in 25 years, that after diligently searching for them for the first time, that's pretty good. And then we've also confirmed that solar systems may be common because we found several stars that have multiple planets orbiting around them. So we think that they may be common as well. But when you come to Earth-like planets, they're not common. In fact, I think the data so far show that the Earth is unique in the universe. Now, that may not jibe with some of the news reports you hear from time to time. From time to time, a few times a year, you'll hear about the latest Earth-like planet found orbiting a star. And usually my job then is to go look at it and see. And it takes me 5 or 10 minutes typically to find out several things that are wrong with them. Many of them are orbiting very close to their parent stars, what we call red dwarf stars. And these planets orbit so closely, they have to because the habitable zone is so close, that they almost certainly are tidally locked. When you orbit close to a large body, the tidal forces raised will lock the planet or the body orbiting so that one side faces the body that you're orbiting. That's happened with the moon. The moon keeps one face towards the Earth all the time. So what would happen on a planet that's like the Earth, or orbiting very close to its parent star, and one side faced that star all the time? Well, obviously the backside of the planet would never get any light, and it would be incredibly cold. Not just cold, but incredibly cold. It'd make Antarctica seem balmy by comparison. And if the Earth were like that, what would happen is much of the liquid water would end up freezing on that backside. And as water evaporated from the hot position on the sunward side, it would migrate to the other side, fall as precipitation, i.e. snow, and collect there. And eventually you would end up with a planet that's barren on one side, burning hot and dry, on the other side, which is frozen and wet, icy all the time. Not a good situation. Also, these stars tend to be very active with star spot activity and magnetic storms that tend to strip atmospheres away from planets. If the planet's not rotating very quickly, it likely won't have a magnetic field very strong to protect it. So consequently, magnetic fields can do that to a point. So these Earth-like planets are supposedly being found. I find a number of problems with each one of them usually. And then I would say that the science so far tells us that there aren't any habitable planets yet. Now, if you would have gone back 30 years ago and surveyed scientists and astronomers particularly and said, okay, if one day we had 4,000 extrasolar planets, how many of those do you think would be Earth-like, proven to be Earth-like? I think most astronomers, most scientists would have said, oh, probably a couple hundred. They would have been extremely optimistic. I don't think anybody saw the possibility that, except for some creationists, of course, I don't think other than that, there were any scientists who saw the possibility that 4,000 extrasolar planets later, that you would have 0 habitable planets. And by the way, I sometimes in my presentations point out that based upon the science here, we can conclude we're probably alone in the universe based on some very good data. I've seen conclusions reached with far, far, far less data than this. Why the paralysis here? Well, it's obvious. It's a heart problem, not a head problem. And so I think the solar system then is unusual to the point of being unique as well. There's certain other design functions, features about the solar system that speak that to us. Okay, last evening, and I'll close with this. Last evening, Professor Wise talked about the Anthropic Principle, and this is the idea that there are a number of coincidences about the universe and indeed about the Earth that seem to make humanity's existence guaranteed or required for humanity's existence. For instance, if you change the amount of charge between the electron and the proton. You would change the structure of matter. If you change some things about nuclear physics, you would change things there, change gravity at all, and on and on and on it goes. These are fundamental things about physics. And if you believe the universe randomly came into existence, there's no reason a priori to think that the universe would have any of the characteristics that it does. And so this thing was coined, this term was coined back, I think, in 1973 by Brandon Carter, talking about this in the cosmological sense. And it's been discussed quite a bit ever since. And in fact, more than 30 years ago, two astronomers named Barrow and Tipler wrote a book. It's entitled The Anthropic Principle. It's a rather thick book. It's got like 1,000+ pages in it. And they give a very thorough history of this, going back way before the term was coined, not nearly a half century ago. They talk about different forms of the anthropic principle. And these they give a great discussion at great length. And finally, when all is said and done, when they got done with their conclusion, they said the universe only appears that way. Yeah, they just discussed tremendous amount of evidence that there's design in the universe. And so the conclusion that one normally would make is that the universe is designed. And they said, no, it's just that the universe appears to be designed. And they go on other ways to try to explain this away. One way they try to get away from it is to talk about the idea of a multiverse. The universe is supposed to be the totality of all existence. And they say, well, there are many, in fact, probably an infinite number of universes out there, all separate and distinct from one another. So they call it a multiverse. And most universes, if they pop into existence randomly, are going to have the deck shuffled in such a way that it's not going to be conducive to life. So it's a selection effect. We're not going to exist. Nobody else is going to exist in a universe where life is not possible. And that's absurd to think that it would be. So the idea is that only in a universe that's suitable for life will life exist. And only in such a universe would beings like us come into existence and then contemplate the world around them and then be in awe of how unusual and how rare and how unique their universe is. But the response is, well, if there's a multiverse, then you shouldn't be surprised because of the selection effect that you happen to be in a universe where life is possible. Now think this through for just a minute. Scientists say this, but just because scientists say something doesn't make it science, doesn't make it true, but it also does not make it science. I could give you an opinion on sports today, but that wouldn't make that a scientific assessment at all. The idea of a multiverse is not testable. There's no science there. Science is supposed to be about creating models and theories, hypotheses that you can test and retest, and discuss and tweak and so forth. How do you go about devising an experiment or observation that where you're going to test the idea that there are other universes out there? Well, if they're truly independent of our universe, you can't, because we're confined to this universe and science only works for us in this universe. So this is not a scientific concept at all, even though scientists talk about it a lot. It's at best a philosophical point or a theological point, but it's hardly science. And many times scientists don't make very good philosophers or theologians. And they need to leave it. They don't like people trying to do science when they're not scientists. Well, maybe they should leave these kind of things to other people who are qualified to make such pronouncements. So, and if anything, this is an escape from science and an escape from reason. It's an attempt to, it's a desperate attempt to try to explain away the inevitable. They're looking at it right there, as Romans 1:20 says, that the evidence that there's a creator is right there in front of us, and yet they reject that truth. It's rational to accept that truth, but the irrational thing is to reject it. And that's a real problem. Again, it's not a head problem. It is a heart problem. It's not a mental or an intellectual problem. It is a spiritual problem. And that is where the battle really is to be fought and to be won, not in science circles so much. We're doing our part, but it's only a part. The main thing is the worldview problem that so many people have.